So good morning, everyone. I'm going to present a paper that is actually the work was done by my student, Kiran Kumar Sappati. So it's a work on a flexible printed carbon dioxide sensor. So let me share my screen and then I can, so that's it. The work is based on a flexible printed acoustic sensor for carbon dioxide sensing. So as we know, there are different kind of gas sensors, and among them, acoustic gas sensors are one kind. So acoustic gas sensors are, there is a lot of work that has been done in this area. And the reason that there is a lot of interest in for gas sensing with acoustic sensors, because they're simple in design. They operate with mass sensitivity principle. And then there is and of course, the acoustic sensors are very, very sensitive to mass sensing, a small mass change on the surface. So that really makes these sensors very highly sensitive towards gases. They have low response time, and you can actually make these acoustic gas sensors to operate both in wired or wireless mode. So that's another big benefit. So if you see acoustic gas sensors, you can see they work in, there are different modes of operation like thickness shear mode, flexural plate wave mode, surface acoustic wave mode. So there are all these different ones. And among them, flexural plate wave mode has lower frequency of operation. And you can actually, for these type of sensors, you can put the GaN sensitive layer either on the interdigitated transducer side or on the other side of the IDT. So that's another thing that is different between surface acoustic wave sensor and the flexural plate wave sensor, because in the surface acoustic wave one, which you see mostly, the gas sensitive layer is placed on the IDT side, but for the flexural plate wave mode, it can be placed on either side of the sensor. So to make our sensor, first we wanted to have a flexible piezoelectric substrate. So if you see, for flexible piezoelectric substrate, there is PDMS that is quite available. But the reason we didn't go with PVDF, because the piezoelectric charge constant of PVDF is very small compared to traditional rigid piezoelectric substrate like quartz or PZT. So we wanted to go for our own piezoelectric substrate that has flexibility, but at the same time, it has good piezoelectric charge constant. So we made our own piezoelectric composite substrate by mixing PZT with PDMS. So here it shows the fabrication process of the PZT-PDMS thin film. So we mix the PZT nanoparticle with PDMS and base and the curing agent, and we stir it or we mix it very well to disperse it well. And then we put that solution on a FR4 board, and then we cure it. And then once we cure it, we can easily peel it off from the FR4 board. And here you can see those small, those very thin PZT PDMS film and how flexible they are. So this film, if you think, so we made a different volume percentage PZT PDMS film. So we mix different volume percentage of PZT. And then this is actually a cross section of 28% volume percentage PZT PDMS film along the thickness, and you can see that the nanoparticle dispersed uniformly in the PDMS matrix. So once we actually made different volume percentage film, we characterize their piezoelectric charge coefficient. So these properties, like Young's modulus, all these things. And we actually found that for 28 volume percentage film, we get a piezoelectric charge coefficient around 78 picocoulomb per Newton, which is still, 3 to 4 times higher than what you get from PVDF film. And also the Young's modulus of 28 volume percentage PZT film was way smaller than PVDF, which shows that it still has way better flexibility than PVDF. So once we have the film, we wanted to design our sensor on it. Something that I didn't mention here is also these films are hydrophobic. So in order to print the, conductive IDT on the piezoelectric PZT-PDMS composite, we actually treated the surface of this thin film with a nitrogen plasma treatment. So I'm not focusing on that side because we already published a paper in that area. So once we have a way to make our film, or once we have our film and we know how to print on them, what pre-printing process we need to do before printing the silver layer, we needed to design our acoustic sensor. So we wanted to go with the flexural plate wave mode because it is highly sensitive. So it has more sensitivity for gas sensing than the other mode. And if you see, most of the people make the gas sensors with surface acoustic wave mode. The reason for that is flexural plate wave mode needs very, very thin substrate, which is difficult to achieve with those conventional rigid, PZT or quartz substrate. But it's easy to achieve that with our PZT-PDMS composite. We can easily make films that are only 100 micron thin. So that's one of the reasons that we could go with the flexural plate wave mode. And the benefit of flexural plate wave mode, it has low frequency of operation. So if you think from the electronics point of view, the electronics that you need to build to excite or receive signal from this sensor, those those electronics will be low cost. The other reason also to do flexural plate wave mode is because the wavelength is large for this sensor. So which means the resolution we need to design the IDTs is not very low. And the reason the resolution is important because we know that the printing process cannot achieve very, very nanometer level or very small resolution that microfabrication can achieve. So, with our resolution of the printer, flexural plate wave mode sensor can still be supported. So that's also another motivation to go with the flexural plate wave mode. So one thing we also found, when we were designing our sensor, that so normally in flexural plate wave mode, people don't put ground plane, but ground plane can actually, if we have a ground plane, conductive ground plane, then it our back plane, it is actually boost the, the back plane really boosts the signal strength of the sensor. And so here is the console simulation with backplane and without the backplane. So you can see we have a larger electric field around the IDT when we have a backplane. So, and the higher signal strength means we're going to have low attenuation, which will translate into high sensitivity for the sensor. So these are the sensor. That's the sensor that we fabricated. So that's the input and output IDT, interdifferentiated transducer. And we have the back plane. And then in between the input and output IDT, we put a multi-wall carbon nanotube layer to sense or as a gas sensing layer for CO2. And we connect some SMA connector on the input and output IDT. And the sensor, in this case, is mounted on a FR4 board in this way. So the resonator response, so once we build this sensor, before putting the multiple carbon nanotube layer, we just wanted to see if the flexural plate wave resonator works. So we connect that to the VNA, and this is the S21 response that we measure. And you can see that we have a resonant frequency around 21.5 megahertz, and the attenuation we achieve there is around minus 3.3 dBm. So then we take the sensor and we expose it to different gas concentration. So you can see here different, so as we expose to different CO2, the resonant frequency changes. And when we take the gas out, the resonant frequency goes back to, the initial state, which shows also the sensor is quite reversible. And the response and recovery time that we got for our sensor is 100 second and 240 second respectively. One thing you can also see that the sensor responds according to the concentration of the CO2. So we measured the response the resonant frequency change for a different concentration of CO2, and for each concentration, we measured it 4 times, and you can see that every time for any concentration, the measurements are very close, which shows that the sensor is very repeatable. And we have sort of a sensitivity for the sensor around 504 hertz per ppm, parts per million, and the limit of detection that we get for the sensor is around 6.7 parts per million. We also wanted to see how much hysteresis the sensor has. So we increase the concentration of the sensor from 0 to 320 parts per million. And then we bring back the concentration again from 320 to 0 parts per million. And you can see that in both directions, the sensor resonant frequency are very, very similar, which really shows that the sensor has very, very low hysteresis. So in conclusion, we have a flexural plate wave carbon dioxide sensor that is printed on flexible substrate. The sensor shows good repeatability, sensitivity, and it has low limit of detection. So the sensor can be easily adaptable to fabricated using roll-to-roll printing, and thus it has a lot of potential for low-cost CO2 sensing. So these are the references, and I'm going to stop here. So I hope so I could present the paper on behalf of my student, yeah, so I want to thank you all for listening to the presentation.